Welcome to the third video recording for the fourth class time set of video instructional material. Today we'll probably be encountering perhaps one of the most difficult constructions of a molecular orbital diagram for a complex molecule, but then hopefully by the end we will see how to construct such a crude molecular orbital diagram with a little more ease and facility. So we're looking at ethylene today, and let's start with half of the molecule, an sp2 carbon called a carbene. So we know that our carbons, the geometry around them is trigonal planar, so we know they're sp2 hybridized, so we could cut the molecule in half and start with a carbene, which is still sp2 hybridized. And so this over here is our triplet carbene. We have one electron in the sp2 orbital over here, and then we have one electron in the p orbital, which goes vertically in the plane of the page. So what is the molecular orbital diagram for our CH2 carbene? Well, we'll start with carbon in the ground state. We've got our 4 valence electrons. We know we're sp2 hybridized. So we have 3 sp2 hybrid atomic orbitals and 1 p orbital, and we'll put 1 electron in each of these sp2 hybrids and p orbitals. And then we'll bring in 2 hydrogens to combine with 2 of the 3 sp2 orbitals, and we form 2 sigma carbon hydrogen bonding molecular orbitals and 2 sigma star carbon hydrogen antibonding molecular orbitals. Of course, we're left over with 1 sp2 hybrid atomic orbital that has 1 electron, and we're left over with the leftover 2p atomic orbital that has 1 electron. So there is the molecular orbital diagram for a triplet carbene. In the next part of this exercise, we're going to bring 2 of these triplet carbenes together to form a double bonded ethylene. And so I will start from the bottom of the page of notes saying, okay, we bring 1 triplet carbene on one side together with a triplet carbene on the other, and we have to merge the molecular orbital diagrams for the triplet carbenes with each other in order to get our ethylene, which kind of makes sense. And so how do we do that? Well, the devil's in the details, right? Here we go. We know our carbene on the right has 2 sigma carbon hydrogen molecular orbitals that are bonding, that are filled with electrons. It's got the 2 sigma star antibonding carbon hydrogen molecular orbitals. We've got 1 sp2 hybrid that has an electron and not an empty 2p, but a 2p orbital that has 1 electron as well. And so we'll bring that together with the carbene on the left, which has the same sort of molecular orbital diagramming. A 2 sigma carbon hydrogen molecular orbitals that are filled, an sp2 hybrid that has 1 electron, a 2p orbital that has 1 electron, and 2 sigma star antibonding carbon hydrogen molecular orbitals that are empty. So if we bring this part together with this triplet carbene, we get the middle molecular orbital diagram, which represents ethylene. So what do we see? We see 4 sigma CH molecular orbitals because each carbene had 2. So now we add them together, we've got 4. We're not reacting them, we're just summing them together. The sp2 hybrids, however, of the triplet carbenes are going to combine. And so since we have 2 sp2 hybrids, well, we'll get a sigma carbon-carbon single type bonding molecular orbital, but we'll also get the sigma star carbon-carbon single bond anti-bonding molecular orbital. When we bring the two 2p atomic orbitals together, we'll get a pi combination where it's bonding, so a pi bonding carbon-carbon molecular orbital. And of course we get a pi anti-bonding carbon-carbon molecular orbital. And the 2 electrons that were in the sp2 hybrids, they go to the sigma bonding carbon-carbon molecular orbital, and similarly the 2 electrons that were each in the 2p atomic orbitals on each triplet carbene go into the pi bonding carbon-carbon molecular orbital. Now this looks very complex, right? But hopefully we'll see on the next page of notes that it would have been not too difficult of an exercise for us to write this crude molecular orbital diagram, just taking into account the hybridization and of the carbons and the number and types of each bond. So here we go, the easy way, right? So it's useful to know the geometry and hybridization of atoms to construct MO diagrams, a crude molecular orbital diagram for ethylene. That's what we just worked through. We know that the carbon is trigonal planar, so it should be sp2 hybridized. We know that we have, what, a total of 4 carbon-hydrogen bonds. We have a carbon-carbon single-like bond, and we have a carbon-carbon double bond, so a pi component. And so to construct the crude molecular orbital diagram, we know we have 4 bonding sigma carbon-hydrogen molecular orbitals, and so if we have 4 bonding sigma carbon-hydrogen molecular orbitals, we must have 4 anti-bonding sigma star carbon-hydrogen molecular orbitals. We've got a sigma carbon-carbon single type molecular orbital, and we know what hybrid molecular orbitals make up that sigma. It's the sp2 hybrid on one carbon overlapping with the sp2 hybrid on the other, and that's a lower energy combination than what? The pi combination. So that would be the leftover 2p on carbon overlapping with another 2p on the other carbon. So a 2p atomic orbital is going to be higher in energy than an sp2 hybrid atomic orbital. Why? Well, the sp2 hybrid atomic orbital has 33% s character, and we know that the 2s atomic orbital is lower than the 2p atomic orbital in energy. And of course, if we have a sigma carbon-carbon single bonding molecular orbital, we've got a sigma star anti-bonding carbon-carbon molecular orbital that's pushed up as high in energy as the sigma bonding molecular orbital is pushed down. And similarly, if we have a pi bonding molecular orbital combination of those two 2p orbitals, we've got a pi star anti-bonding carbon-carbon molecular orbital. So hopefully constructing this crude molecular orbital diagram, just realizing the hybridization on the carbon and the number and types of bonds that we have, wasn't that difficult, and you will be able to extend that to other molecules that have multiple bonds, understanding the hybridization on the carbon atoms or the heteroatoms that occur in those molecules. And of course, practice is something that helps, right? Don't be afraid to practice drawing something out, make mistakes, and learn from those exercises. The important part of this diagram, the sort of central part that we like to take note of, is something called the highest occupied molecular orbital, the HOMO, and the lowest unoccupied molecular orbital, the LUMO. Highest in what and lowest in what? Well, highest in energy. This is the highest in energy occupied molecular orbital, and that's the lowest in energy unoccupied molecular orbital. Why are these important? Well, these are the two faces that this molecule presents to the world, just like atoms in general chemistry would react based on how many valence electrons they possessed or how many vacancies in their valence shell they possessed. Molecules are much the same. They can present electrons to the world, and those will be the electrons that are least tightly held, that is the highest energy electrons, which exist in the highest occupied molecular orbital. And similarly, molecules can accept electrons into the lowest unoccupied molecular orbital because it's empty, so they can take electrons there. So I think that pretty much finishes this video. We will finish up our Class 4 instructional video session with the next one.